Okay, online students, go ahead and pause your video here and take a few minutes to try these 4 practice problems. So these are the practice problems 1, 2, 3, and 4. So pause your video now and try those, and then start the video again when you're ready to check. All right, so number 1, this one looked really good. The notation is f minus g of x. So this means we're doing f of x minus g of x. So f of x is 5x minus 4, and g of x is 2x plus 7. When we subtract, we do have to be careful of our numbers, and most of you did get this. We should have got 3x minus 11 for number 1. All right, number 2, this one we had to plug in a number. Same thing, we mostly did really good with this one. F plus g of 3 means we're finding f of 3 plus g of 3. So f of 3 means plug in 3 into f of x. 5 times 3 minus 4 gives us 11. G of 3 means plug in 3 into function g. So 2 times 3 plus 7 gives us 13. And so then when we add those together, we get 24. So on this one, since our input was a number, our output should be a number. Where on number 1, our input, we were still working with x, so our output still had x's. Number 3, I was glad to see most of you remembered this notation as well. We say that as f of g of x, and we can rewrite it as f, and then in parentheses, g of x, so we keep the letters in the same order. This one is telling us we plug g of x, that's the input, and we're plugging it in to function f. So it looks like this. F of x is 5x minus 4, but instead of x, we're filling in 2x plus 7. Okay. And then to distribute, or to simplify, we just have to distribute the 5 and then subtract the 4. So we end up with 10x plus 31. Okay, so those 3 all looked good. Some of you are still working on this last one, but let's make sure we know what that is saying as well. This one, g of f of negative 4, if I rewrite this in function notation, it looks like this, g, and then in parentheses, f of negative 4. If I do the f of negative 4 part first, that means plug in negative 4 into function f. So 5 times negative 4 minus 4, that gives us negative 20 minus 4, so that gives us negative 24. So then we take this output. Remember, we're taking the output and plugging it into function g. So now I'm plugging negative 24 into function g. So it looks like this, 2 times negative 24 plus 7, negative 48 plus 7 should give us negative 41. Okay, so 1, 2, and 3 actually looked really good. The one that was not as good, or some of you didn't get there yet, was number 4. We should have got negative 41. Okay, so those are all some of the different operations from 2f. We would also have multiplying and dividing to combine to get 2 new functions, but we didn't do that part yet. So now we are starting our next section, and this is our last section in Unit 2. So we are going to spend a lot of the time today taking notes in section 2G. So if you have your note packet, either you came to pick it up or you printed it, in the note packet. If you don't, I do have some of those note packets. So if you want to get it out, if not, I'll put it on. So our last thing, our last learning target of dealing with functions is dealing with inverse functions. So here's our learning target. I can determine, verify, and graph inverse functions of one-to-one functions. So when we're thinking about an inverse function is going to do the opposite of a function. So it undoes a function. So first, before we actually write anything in the notes, let's think about inverse operations. First of all, if your phones are distracting you, please put them away. I know when you were online, no one was there to tell you to put your phones away, but you got to make sure you're paying attention so we can hopefully go through this fairly quickly. So an example of an inverse function. So let's say here's our operation. We already know what inverse operations are. So say we're adding 3. What's the opposite of adding 3? Subtracting 3 would be the inverse operation. Or if we're multiplying by 5, what's the opposite of multiplying? Dividing by 5. So we already know that. Let's see if we remember this. What's the opposite of something squared? So for example, 6 squared. What's the opposite operation of squared? Square root. So square root, 6 squared would be 36. The opposite would be a square root. So that's what we're dealing with when we're doing inverse functions, is we're having to do an inverse operation, but we also have to do it in the opposite order. So opposite order is important as well, because for example, in the morning when you get dressed, most of you probably put your pants on first, and then your socks, and then your shoes. I don't know anyone who puts their shoes on and then their pants on, but I guess it could happen. So at night when you're getting undressed, so this is when you're getting dressed, undressed, you'd have to do this in the opposite order, right? You'd have to take the shoes off, and then you have to take the socks off, and then you have to take the pants off. So in order to get undressed, you also have to do it in the opposite order. Same thing when we do functions. We're doing the inverse operation, but we also have to think about the order that we're doing them in so that we get the opposite or inverse function. Now let's start filling this in. So again, make sure you're filling it in on the notes. Joseph, put your phone away, please. So an inverse of a relation is just, there's some kind of relation between inputs and outputs, but it's not necessarily a function. So an inverse of a relation is the opposite of a function. So normally we have input, output. The inverse is the other way around. The inverse is output to input. So for example, I'm just making up numbers. In a relation, if our input is 3 and that gives an output of 10, on the inverse relation, an input of 10 would give an output of 3. Okay, so it switches the input and the output. So the notation, again, usually it's the notation that's challenging in these. The notation, the inverse of a relation are we're going to use function notation, but the notation we use for inverse in general, so we're saying R is the relation, we use a little -1. So it's not a -1 power, that's just the notation we use. It looks like a -1 power, we write it in the superscript, but that is how we write this, but we say R inverse. So we don't say R to the -1, this means R inverse. And we'll see what it looks like with a function as well. So here's an example. Give the inverse of this relation R below. So remember when we have coordinate points, those are the inputs and the output, input, output. So if the original has an input of 0 gives an output of -7, the inverse, notice this notation is the inverse, is going to be an input of -7 gives an output of 0. Okay. So instead of 0, -7, we have -7, 0. The signs don't change, so it's still -7. We just switch the order and put an output switch. So instead of -1, 2, the inverse would have 2, -1. Instead of -4, -2, I switch the input and output. So that one would be -2, -4. And instead of 6, 3, my output would be, or my coordinate point would be 3, 6. Okay, so on an inverse, the input and output are switching. Okay, so that just has to do with any relation. Now specifically talking about functions. So the definition of function, we talked about it a lot in the fall semester. On a function, each input has one output. On a one-to-one function specifically, each input has a unique output. So one-to-one function, each input has a unique output. So what that means, when we just have a function, each input has to have an output, but the outputs can be the same. On a one-to-one function, none of the outputs are the same. They're all unique outputs. So each input has a unique output means that all the outputs are different. Okay, that's going to be important when we're talking about functions, or inverse functions, I should say. So hopefully we remember, so recall, the vertical line test is used to determine whether a relation is a function given a graph. So the vertical line test says any vertical line should cross the graph only once if it's a function. So the horizontal line test is used to determine whether the inverse of a relation is a function. The horizontal line test is used to determine whether the inverse of a relation is a function. Now this is important, and this is why we have to figure out if a function is one-to-one. Both the relation and its inverse must be a function in order to be a one-to-one function. Now going in line with this, in order to have an inverse, a function has to be one-to-one. If a function is not one-to-one, it doesn't have an inverse, or at least it doesn't have an inverse on the whole domain. Okay, so the first examples we're going to do are going to be determine whether the relations are one-to-one functions. Okay, so first of all, we should know that each graph is a function. So to be a function, the graph should pass the vertical line test. So that means a vertical line should cross only once. Okay, so if we look at number one, it is a vertical line, or it is a function because the vertical line only crosses once. But now we need to check if it's one-to-one. That's where we use the horizontal line test. This is Miss Williams. He is not here. No, no problem. Bye. So now let's check the horizontal line test. So a horizontal line should also only cross the graph once. Okay, so a horizontal line does cross the graph only one time, no matter where I put the horizontal line. So number one is, it is a function and it's also one-to-one. So number one is a one-to-one function. Number one is a one-to-one function. So what that means is this function does have an inverse. All right, so number two, first question we want to ask ourselves, is it a function? So number two, to see if this is a function, we would use the vertical line test. So this one is a function, but now we want to know, is it one-to-one? Oops, let me find my lines. So if I put a horizontal line through this graph, notice it's crossing the graph multiple times. It crosses here, 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 here. So this graph, number two, is a function because it passes the vertical line test, but it is not one-to-one. Okay, so this one is a function, but it is not one-to-one. So number two is a function, but not a one-to-one function. So why that's important is because that means that this function does not have an inverse unless we restrict the domain or only use part of the function. So if I'm trying to find an inverse, I can't use the entire function. I can only use a portion of the function. Otherwise, it's not one-to-one. All right, let's look at number three. So number three, it's important to kind of recognize what is happening on this graph. And I know we saw a lot of these types of functions in 2a and 2b. This graph has asymptotes. So remember, that's where the graph is getting close to those lines, but never actually touching. Let me draw those in real quick. That's going to be important when we're thinking about whether this is one-to-one or not. Okay, so the graph is getting close to those lines, but not touching. So first question, is this a function? And the answer for that is yes. It is going to pass the vertical line test. Anywhere we put a vertical line, it will cross the graph only once. But then we also want to ask the question, is it one-to-one? So does it also pass the horizontal line test? So if I put a horizontal line anywhere on the graph, it is only going to cross once. So this one also is one-to-one. Even here, the graph won't cross at all. It doesn't cross more than once. Sorry, my line's not very straight, but you get the idea. So this one, number three, is a function, and it is one-to-one. So this one does have an inverse. So number three is a function and it is one-to-one. So it does have an inverse. Okay, so let's look at 4, 5, and 6. So first we want to see if we have a function. Number 4, vertical line test. This is good for the vertical line test. So this one is a function, but now we want to know, is it one-to-one? So that means we want to check the horizontal line test. We want to know if a horizontal line only crosses once. So here, the horizontal line is only crossing once. Even if I move my horizontal line around, same thing, it's only going to cross the graph one time. So number 4 is a function, and it is one-to-one. So that means it has an inverse. So number 4 is a function, and it is one-to-one. Okay, so number 5, this one is our graph here. It's kind of hard to see up here, but you hopefully can see it on your papers. This one is a horizontal line, almost said the wrong thing. So if we check if it is a function, it is a function because it passes the vertical line test. A vertical line only crosses once. So number 5 is a function, but we want to ask ourselves, is it one-to-one? Now, this one, in most places that I put a vertical line, it doesn't cross at all. But, or sorry, horizontal line, we're doing the horizontal line test. If I put the horizontal line here, it crosses at every single point, which definitely means it's crossing more than once. So this one is definitely not one-to-one. All right, so number 5 is a function, but it is not one-to-one. That means it doesn't have an inverse. So number 5 is a function, but there's no inverse of that. All right, and then the last one, number 6. First, we want to do the vertical line test to see if this is a function. All right, so what do you guys notice on this one? Is this one a function? This one is not even a function because it doesn't pass the vertical line test. The vertical line crosses more than once. So this one is not a function. So if it's not a function, do you think I have to bother to check if it's one-to-one? No, because if it's not a function, obviously it can't be a one-to-one function. So I don't even have to do the horizontal line test on this one because it can't be a one-to-one function because it's not a function. Okay, so all the first 5 were functions, and some were one-to-one and some were not. The reason that's important is because if a function is one-to-one, it does have an inverse. If a function is not one-to-one, it does not have an inverse. Okay, so now let's actually find some inverse functions. So go ahead and turn the page in your notes. There you go. Yeah, can you wait till we at least make a couple examples? Okay, just so you have some down. So maybe after. Okay, so the notation, again, this is where we have to know what we're being asked, so we have to recognize what the notation is. So an inverse function, the notation of an inverse function, when we use function notation, it looks like this, f of x. The notation for the inverse function, we still use the f of x, but on the f, we put a little -1, like we did with the relation. So it looks like this, f with this little -1 in the superscript of x. We don't say it as f -1, we say it as f inverse of x. Okay, so that's how we say this, f inverse of x. Okay. And as we talked about, not all functions have inverse functions. Okay. Or we have to restrict the domain so that we can find the inverse function. So here's the steps to finding the inverse functions. It's already filled in here for us. So to find an inverse function, if we know a function has an inverse, we're going to replace f of x with y. So instead of f of x, remember we could write y as the output. The only reason we do that is just because we're more familiar with working with x and y. Not that we really need to. Then remember when we have an inverse, the input and output switch. So then we interchange x and y. So we switch x and y, which would be our inverse function. It just wouldn't be in the correct form. So then we solve for y, so we get the y by itself. And then we rewrite y as f inverse of x. Okay, so let's go ahead and do that on these examples here. So number 7, we have f of x equals 4x minus 8. We hopefully can recognize what kind of function that is. This just has x to the first power, so this is just a linear function. So its graph would just be a line. So that is going to be a one-to-one function, which means it does have an inverse. Okay, so now let's actually find the inverse. The first thing we want to do is we want to rewrite f of x. Remember, we can use x and f of x as the input and output, or we can also use x and y. So the first thing I usually do is instead of f of x, I'm going to rewrite this as y equals 4x minus 8. So I haven't done any algebra yet. All I did was rewrite f of x with y. That's the first step. So y equals 4x minus 8. Now, to find an inverse function, we switch the input and the output. So I'm going to switch or interchange the x and y. Not any of the other variables or numbers or operations, just x and y. So when I switch x and y, it looks like this. X equals 4y minus 8. Okay, so what we did there, we switched x and y. Everyone see where that's coming from? Okay. Now, technically, these two functions, or these two functions are inverses of each other already. So this is the inverse, but it's just not in the right form, because in order to put it back in function notation, we need the output by itself. So now I have to get this y, I have to solve for y and get the y by itself. So that's where we have to use our algebra skills. So far, we haven't had to do any algebra, but now I do. So now we want to isolate the y or get the y by itself. So to get this y by itself, I need to, I'm going to have to get rid of the 4 and the minus 8. We want to make sure we do the right thing first, though. I want to get rid of the minus 8 first. So to get rid of minus 8, I do the inverse operation. So I would add 8. And of course, it's an equation. Whatever we do to one side, we do to the other. So I'm adding 8 to both sides. That gets rid of this. And now on the left side, we have x plus 8. I can't combine those, so I just write it like that. X plus 8 equals 4y. Okay, now I'm still trying to get the y by itself. So now I have to get rid of the 4. So I have to do the inverse operation. This is 4 times y. So to get rid of multiplying by 4, I would have to divide by 4. And there's a couple ways we can write this. I'm going to show you a couple different ways we can write this. But I have to put this whole thing over 4. Okay, so now that gets rid of that 4, and now the y is by itself. So we have x plus 8 over 4 equals y. When we write it Oftentimes we write it with the y by itself on the other side of the equation, on the left side. So I can rewrite this as y equals x plus 8 over 4. I just put it on the other side of the equal sign. And now, to get our final answer, this is our final answer. We just want to use the same kind of notation we started with. We started with f of x equals 4x minus 8. This is now the inverse function. So I would say, now I replace the y with the inverse notation. F inverse of x equals x plus 8 over 4. Okay, and that's our inverse function. Okay, so the algebra itself wasn't too hard there. We just were trying to get the y by itself. Okay. So what that means is if I plug in a number here, for example, I can pick any number. So if I plug in a 3 for x, my output would be 4. But here, if I plug in a 4 for x, my output would be 3. So the input and output switch. Now, a couple other ways we can write this. The way you write your final answer doesn't really matter so much, but I just want to show you so you can recognize they're the same. So on this, we have y equals x plus 8 over 4. Instead of dividing the whole thing by 4, you could have divided each part separately by 4, like this. X over 4 plus 8 over 4. This you could leave it as a fraction. Either you could put it as x over 4 or 1/4 x, but this would divide to give us a 2. So you could also write it like this. So you can simplify or you can leave it as a fraction like this. They're both the same thing. Okay, so let's look at number 8. Number 8, we have f of x equals 1/2 x cubed minus 1. So that one has an x cubed. We talked about inverse operations kind of at the beginning, and we said that the inverse operation of something squared, I'm going to just write it off to the side to remind us. Inverse operations, when we had x squared, the inverse of that is square root of x. So an x squared and a square root of x get rid of each other. Those are inverses. So this one has an x cubed though. Does anyone remember what the inverse operation of an x cubed is? We got to know that in order to do this problem. A cube root, exactly. So the inverse operation of x cubed is a cube root. Okay. So that's important to know in order, otherwise we can't do this problem. All right, so number 8. Now let's actually find the inverse. So we have f of x equals 1/2 x cubed minus 1. And we're trying to find the inverse. The cubic functions, we looked at the graph of those in 2D. The cubic functions are like these squiggle functions. So that one is a 1-to-1 function. So it does have an inverse. Okay, so now let's actually find the inverse. All right, so the first step is just to help us with the notation. Instead of f of x, we're going to write y equals. So I'm just going to write this as y equals 1/2 x cubed minus 1. Okay, so that's step 1. All we do is replace f of x with y, just because we're more used to working with x and y. Now here's the place where we actually find the inverse. To find the inverse, we need to switch x and y. That's what gives us an inverse function. So when I switch x and y, I don't switch anything else. It looks like this. X equals 1/2 y cubed minus 1. Okay, so all I did there was switch x and y. So we have x equals 1/2 y cubed minus 1. Okay, then this is the inverse. It's just not in the right form. So I need to get the y by itself in order for this to be in the right form. So now I'm going to solve for y, which means get the y by itself or isolate the y. Okay. There again is a couple ways we can think of to do that. If I'm trying to get the y by itself, I'm going to have to get rid of the half that it's multiplied by, the cubed, and the minus 1. The first thing we do is get rid of the minus 1. So to get rid of the minus 1, I would add 1. And of course, it's an equation. So whatever we do to one side, we do to the other. So I'm adding 1 to both sides. This side becomes x plus 1 equals 1/2 y cubed. Okay. Now the half in the front, there's a couple ways we can think about this. This is multiplied by a half, so you could divide by a half, but we don't want to leave a fraction in a fraction. We never want to leave a fraction in a fraction. So let's think back about how we get rid of fractions. The way to get rid of fractions is to multiply by the LCD. Here, the only denominator is 2. So to get rid of the fraction, I can multiply by 2, which is the LCD. But if I multiply this side by 2, I have to multiply this side by 2. So I'm multiplying both sides by 2, because here 2 times a half, that would just be a 1. So I get rid of the fraction there. On this side, you can distribute the 2, but for now, I'm just going to leave it in parentheses so we can see how it compares to our original function when we're done. Okay, so now we multiply by 2 to get rid of the fraction. So we have 2 times x plus 1 equals y cubed. Now I can get rid of the cubed part. That's where we have to use the inverse operation. So to get rid of the cubed, we need to do a cube root. So I'm doing a cube root of this side. And of course, whatever I do to one side, we do to the other. So I have to do a cube root of this side as well. Okay, so on this side, the right side, the cube root and cube get rid of each other. And now the y is by itself, which is what we want. And then on this side, we have cube root of 2 times x plus 1. Okay, so let's write that. So we have y equals cube root of 2 times x plus 1. And the last thing I would do, instead of writing y, we want to use the same notation that we started with. So I'm going to use function notation. F inverse of x equals cube root of 2 times x plus 1. Okay, and that's how we would write our final answer. So, like I said here, you could also distribute the 2, but the reason I just left it as 2 and then in parentheses x plus 1, because then we can see more easily how it's related to this. Okay, so let's look at our function and our inverse. You don't need to write this part down, but just to make sure it makes sense, on this function, if I'm using on the original, if I'm using order of operations, the first thing I do is cube the function, then I multiply by half, and then I subtract 1. So that's on our function. So again, don't write this down, but just so we can make sure we understand. We did the cube first, and then we multiplied by a half, and then we subtracted 1. Now remember, when we do the inverse, we have to do things in the opposite operation. Oops, I already erased it. But just like when we talked about putting your socks on and then your shoes on, to take them off, you have to take your shoes off first and then your socks. Same thing here, we have to do the opposite. So on this one, our last operation was subtracting 1. So on the inverse, our first operation is the inverse of this last one. The opposite of subtracting 1 would be adding 1. Then we go, because we're going in reverse order. The opposite of multiplying by a half technically is dividing by a half, but we got rid of the fraction. So here, multiplied by 2. And then the last is the getting rid of the cube. The inverse of the cube is the cube root. Okay, so in our original function, we went in this order. On our inverse function, we have to go in reverse order to get rid of these. Okay. So that's why the order we do these in does matter. Okay, so here we can see in our inverse function, we would add 1 first, multiply by 2, and then do the cube root. Okay, so let's stop there for right now and do some practice. Before we do some practice, you guys want to step outside and do a math break? Or yeah, okay. Let's just go take a step outside for just a minute. So we can, first of all, get up, but also to take a break, take a math break.